Welcome and thank you for joining me. Here we're going to take a look at a practice question from lesson U2A3, number 14. In this question, we are given the equations of two planes, pi1 and pi2. We would like to prove that these two equations represent the same plane. First, we're going to visit each and every equation and try to make sense of all these numbers given in here. And it is best that we start off with a general form of the equation of a plane. Recall that any plane can be indicated by letter pi. We'll have the equation r. Vector r is any vector on plane pi equals vector r0, which we call the starting vector on the plane, plus the sum of two direction vectors, direction vector A and direction vector B. So we take the sum of two direction vectors and we stick a scalar to each of them. So TA and TB. So S and T will be real numbers. Remember that for the direction vectors, it doesn't matter what size they have, and that's why you have the scalars S and T. What matters is their directions, which will help us identify the location of the plane pi. Now, R0 obviously is described by some coordinates, three coordinates in 3D, x0, y0, z0. We will see the coordinates of vector A multiplied by some scalar, and then we'll see the coordinates of vector B multiplied by some scalar, again, in this case, t. So now let's revisit every equation and check and see what we have here. As you can see in here, you see the scalars u and v, and that makes us think that these two must be the direction vectors. So I will call them direction vectors A1 and B1. Notice that we do not see here a starting vector, which makes us think that the starting vector must have been or must have had the coordinate 0, 0, 0. Which means that this plane passes through the origin. And when that happens, you do not need to write the coordinates of the starting vector. In a similar way, we can reason about the second plane, so R2 will be any vector on plane pi2. And we notice that in this equation, we have the coordinates of two vectors multiplied by a scalar. So that makes us think that these must be the direction vectors, which we will call A2 and B2. And S and T are scalars. Similar to the first equation, here we do not see the starting vector R0, which again will make us think that R0 is at 0, 0, 0, which means that both planes pass through the same point, through the origin. So at this point, we would like to think, what makes two equations represent the same plane? Remember that A1 and B1 are already on the same plane. And what I'm going to do is I'm going to draw two vectors, A1 and B1. So let this one be A1 and this one be 1. Now, we also know that vectors A2 and B2 also lie on the same plane. If we want to prove that these two equations represent the same plane, then it is enough that we prove that A2 lies on the plane of A1 and B1, or B2 lies on the plane of A1 and B1. And similarly, we can prove that A1 lies on the same plane as A2, B2, or B1 lies on the same plane as A2, B2. Because if this is right, then A1 will follow B1, right? So in other words, or in simpler words, then we're going to say that if the coordinates of any of the direction vectors from the second equation satisfies the first equation, it means that this direction vector will fit into this equation, which means that it will lie on the same plane as A1 and B1. Now, it doesn't matter which pairs or how you arrange the vectors. So you can substitute A2 into the equation of pi 1 or B2 into the equation of pi 1. And similarly, you can substitute A1 into the equation of pi 2 or B1 into the equation of R2 or pi 2. So in this case, I'm going to choose to use vector A1 and substitute it into the equation of pi 2. Just for the fun of it, what you may want to do is try any other arrangements other than the one that I am trying here. So I'm going to write in here that if A1 is on pi 2, then it must satisfy the equation of pi 2. What that means is that if we substituted the coordinates negative 3, 2, and 4 for any vector on pi 2, then we would have we would have negative 3, 2, 4 equals S, negative 1, 5, negative 3, plus T, negative 1, negative 5, 7. If we're able to find two possible values of S and T, or a possible value of S and a possible value of T that can satisfy or help this point fit in the equation, then we would say that both equations represent the same plane. So let's get started. So here we have the x coordinates. So we have negative 3 equals negative S minus T. The next one is the y coordinate, which must be 2 equals 5S minus 5T. And lastly, we have the z coordinate, which must equal or must fit in the parametric equation 4 equals negative 3S plus 7T. Now we have to find S and T, and remember that we have 1, 2, 3 equations built. We can use any pair of equations to solve for S and T, and then with the found values of S and T, we can test and see if they work for the third equation. So let's get started. I will call this equation 1, this one 2, and this one is equation 3. So equation 1 can be written also as S plus T equals 3. Equation 2 is 5S minus 5T equals 2. I would like to solve by using elimination method, which means that I will need to multiply the first equation by 5. So this will give 5T plus 5S equals 15. And in the denominator, we have 5S minus 5T equals 2. In order to eliminate one of the variables, if I want to eliminate actually the variable T, I can just add. If I want to eliminate variable S, I can subtract. I choose addition, and this will give us 10S plus 0T equals 17. That will give the value of S 17 over 10. With this S value, we are going to use equation 1 to solve for the value of T. So S plus T equals 3, means that 17 over 10 plus t equals 3, which means t equals 3 minus 17 over 10, or t equals 30 minus 17 over 10. So we figured out that the values of s and t are 17 over 10 and 13 over 10. So with these two values, we're going to visit the third equation to check and see if they would satisfy equation 3, where we have 4 equals negative 3. The s value is 17 over 10, plus 7, the t value, which is 13 over 10. So we are going to simplify the right side until we check and see, and then check and see if it equals 4. So that would be equal to negative 3 times 17. It's negative 51 over 10. 7 times 13, that would be 91 over 10. That would equal negative 51 plus 91 over 10, or 40 over 10, which is 4. So it seems that these two values for s and t respectively would satisfy the third equation. And that tells us that point negative 3, 2, 4, or the direction vector a1, fits into the second equation, which means that direction vector a1 lies on plane pi 2. If a1 lies on pi 2, b1, which already lies on the same plane as a1, must be on plane pi 2. So therefore, we're going to say that planes pi 1 or the equations of pi 1 and pi 2 represent the same plane. There are multiple ways of solving this problem. And the second method that I would like to share with you is another method that one of the students came up with. So I'm going to get started. If you would like to, out of curiosity, to listen to the second explanation, that would be